thank you. And thank you to the organizers for having me here today. So this is going to pick up exactly where Jara's talk left off. So you've just heard that there are various scenarios under which you might accumulate oxygen abiotically. Fortunately, there are other observations you could make to discriminate, hopefully, these scenarios from the true biological cases. But there's still a limitation here, right? In the sense that even if life is common in the cosmos, that's no guarantee that oxygen biosignatures are common. We heard from Bob Blankenship earlier this week that we really don't know if oxygenic photosynthesis is likely to have evolved elsewhere. It's a very complicated metabolism. It only evolved once here on Earth. And even if it did, right, even if oxygenic photosynthesis does commonly evolve, that's still no guarantee of common oxygen biosignatures. We know that just from Earth's own history, right? Despite the origin of life very early on, the probable origin of oxygenic photosynthesis very early on, it took a long time for modern, readily detectable levels of oxygen to accumulate. And so to avoid missing planets like the early Earth, right, to avoid the kind of false negative situation where you don't see oxygen, you assume there's no life, it'd be good to have some alternatives. And so Stephanie has already introduced one approach to looking for alternative biosignatures, this idea of chemical disequilibrium, the coexistence of incompatible species. And so just to remind you, right, the canonical example of that, oxygen and methane in Earth's atmosphere, the chemistry predicts these two species should react to form CO2 and water very rapidly, on sort of decade timescales, depleting the atmosphere of methane quickly. The fact that this does not occur is because both methane and oxygen are being continuously replenished by life, right? And so crucially, the coexistence of these two species in the modern Earth's atmosphere is a more compelling biosignature than oxygen alone because of the need for large replenishing fluxes and the difficulty explaining those large replenishing fluxes without biology. All right, so we have this idea of chemical disequilibrium. It's a bit nebulous, so one thing you might want to do is try and quantify it, right? Here's the simplest, and just to see, how well does this work. So the simplest thing you can do is take an atmosphere, here's our box of atmosphere here, react that thing to equilibrium, do that computationally, say with Gibbs energy minimization, so various species change, you get some final state, and then you can quantify the size of the disequilibrium by the difference in the Gibbs free energy between what you started with and what you finished with, right? That's the simplest possible way to measure the disequilibrium. The larger it is, the further the atmosphere is from equilibrium. So if you do that for solar system planets, right, this is what you get, comparing that size of the disequilibrium. And unsurprisingly, Earth's disequilibrium is the largest of the solar system planets, but not because of the oxygen-methane pair, as you might expect. It's a relatively small contributor. The largest contribution is that reaction up there, the coexistence of nitrogen, oxygen, and liquid water. These three things should not coexist. They should react to form nitric acid in solution. And there's a lot of energy locked up in those three species. And of course, this is biogenic, right? The reason you have biological. So this causes Earth's disequilibrium to be much larger than the abiotic disequilibrium of other solar system planets. And so, excuse me, in this paper, we argue that the coexistence of those three species is a more compelling biosignature than oxygen alone. Right, but whether it's oxygen, nitrogen, or water, or oxygen, ozone, and methane, both of these things are kind of variations on oxygen as a biosignature, right? And the reason we started talking about this equilibrium as a biosignature was to try and go beyond oxygen as a biosignature because of Earth's history, because of these times in the early Earth when we didn't have a lot of oxygen around. So what we thought we'd do was apply this disequilibrium idea to the Earth through time to see if it reveals anything else that could be useful, combinations of gases on the early Earth that might reveal the presence of life. And so I'll just skip to kind of the key result, which is applying the calculations to the very early Earth, the Archean, when there was virtually no oxygen around. And so here is that calculation. This is probably the busiest figure I'll show you, so bear with me. But basically, we're plotting abundances, right? So the top plot is stuff in the atmosphere, and the bottom plot is things in the ocean. Fortunately, for remote sensing purposes, it doesn't really matter what you assume about what's in the ocean. And then the blue bars are what we assume the abundances were on the early Earth, the true abundances. There's some uncertainty on that, but you can do a range. And then the green is what we calculate, what the abundances would be in thermodynamic equilibrium. And so you'll notice in the top figure, there's a dramatic change in methane. The methane shouldn't be there, right? So it's a log scale. So basically the methane is disappearing when you react the Archean Earth system to equilibrium. And when you dive into the stoichiometry, you figure out that this is the reaction that's going on. Essentially, CO2 and methane should not coexist in a nitrogen-dominated atmosphere with water. They should react to form ammonium and bicarbonate in the ocean, depleting the atmosphere of methane. And there's a fair amount of energy associated with this, a large available energy. And importantly, it's biogenic, right? The reason we think there was so much methane in the Archean atmosphere to begin with is because of biological production. So you have this potential disequilibrium biosignature. And if you plot the magnitude of Earth's disequilibrium through time, you get a figure something like this, where the disequilibrium is increasing through time. It's CO2, methane dominated on the early Earth, and then oxygen dominated after that. An important point I want to make, though, is you can overplot the disequilibrium value of modern Mars, and it goes right through the middle, which is to say that this number on the y-axis, the size of the disequilibrium, is not in and of itself diagnostic of life, right? The interpretation matters. If you want to say disequilibrium is attributable to biology, you really have to look at the species involved and ask, well, what is required of replenishing fluxes? Is that plausible without life? And so with that in mind, kind of the obvious question to ask, right, is like, okay, methane, CO2, a biosignature on the early Earth. If you were to find that elsewhere on an exoplanet, would that be a good biosignature? There's some reason to think so. As we've heard, methanogenesis is a relatively simple ancient metabolism. It should be easy to do. If you have common outgassing products, CO2 and hydrogen, you've got some water around, a habitable environment, these things should just grow. It should be easy. Importantly, methane has a short lifetime in terrestrial planet atmospheres. It should be photodissociated and destroyed within tens of thousands of years. And so you really need a large replenishing flux of methane to maintain such an atmosphere. And so the question then becomes, well, could you have large abiotic fluxes of methane into such an atmosphere? And so Stephanie talked about this a little bit, but I'm going to do a slightly deeper dive on some of these false positive scenarios for methane CO2 biosignatures. So here are the obvious ways you could do it, right? Could you just outgas a lot of methane? On the Earth today, virtually no methane comes out of volcanoes that isn't associated with previously buried organic matter. And this is because Earth's mantle is relatively oxidizing. And so when carbon comes out, it comes out mostly as CO2. Right? So you've got CO2 and methane, opposite ends of the oxidation spectrum. CO2, carbon in its most oxidized form, methane, carbon in its least oxidized form. You can imagine a planet with a mantle redox is shifted towards methane, so you have more methane coming out. But if you do that, you must necessarily go through the intermediate redox state of carbon monoxide. So you'd expect such planets to build up or to outgas a lot of CO. And so this is something you can quantify, and this is work led by Nick Wogat, another grad student at UW, where we just sort of ask the question, well, what's the range of possibilities for outgassing for terrestrial planets? That's a hard general problem, but if you just care about the carbon species, it's not so terrible. And so you can just sweep the parameter space of different host rock compositions, different magma chamber pressures and temperatures, and different amounts of ocean overburden pressure above your magma chambers. And what you get out from that is the outgassing ratios, right? How much CO you're outgassing per CO2, how much CO to methane. And so when you do that parameter space sweep, I should say that what you don't want is both of these things to be low, right? If both these ratios are low, then you're looking at a false positive, which is hard to distinguish. This is the answer you get, CO to methane on the x-axis, CO to CO2 on the y-axis, Earth falls somewhere over there. This is the kind of the danger zone, right? This is the situations you might mistake for biology. It's hard to get there from outgassing. Sure, you can have a more reducing mantle. You push your Earth kind of to the left, you outgas more methane, but then you're outgassing more CO. And so it's pretty hard to do this. So I don't think a pure outgassing false positive is likely. What about impacts? So we heard earlier in the week that if you hit a planet with large enough rock or reducing rock, then you can make a lot of methane for a time, right? That's the crucial point. This is transient. Even for the largest of impacts, the methane would hang around for tens of millions of years. And also those scenarios tend to produce a lot of carbon monoxide as well. So you could probably tell that that was going on. You might be able to do some interesting things with very volatile rich bodies, right? So you take a Titan-like planet, you melt it, you put it in the habitable zone. What does that look like? Could you get a methane CO2 false positive in that case? You can run that thought experiment and do those calculations. And, you know, based on inventories of what volatile inventories of what we think Titan is made of. And again, for a time, yes, you could get a methane CO2 atmosphere, but it doesn't hang around for long. So the table down the bottom shows basically how long the methane lasts for different weight percent volatiles for your planet. Even for planets that are a few percent volatiles by mass, the methane hangs around for sort of tens of millions of years. And if you get even more volatile rich, you're starting to get to the point where you can tell you're looking at a volatile rich planet just from the mass and radius observation. So I think this is unlikely to generate a false positive that would hang around for very long. There might be interesting things you could do with class rates, and we could discuss that, but I think it's pretty difficult to do. So this leaves you with what I think is the most plausible false positive for a methane CO2 biosignature. This process of serpentinization, which was talked about by Jennifer Glass earlier this week, and I've borrowed her figures here. So the serpentinization part occurs in oceanic crust, rock reacts with water, makes hydrogen gas, and that hydrogen gas can then combine with CO2 to produce methane abiotically. This happens on Earth today, but by most estimates, the amount of methane produced by this abiotic process is orders of magnitude smaller than what is made by life. But could you scale it up on some other terrestrial planet? And you can do some kind of back of the envelope calculations for this, where you say, right, the amount of methane you can make through serpentinization is going to depend on a few factors. This is like a Drake equation style thing. You say, all right, it's going to depend on how much crust is being made to oxidize, right? And then what is the iron content of that crust? And then of that iron, how much actually gets turned to hydrogen? And of that, how much actually gets turned to methane? And if you take very generous estimates for what these things could be, then you get out this probability distribution for the maximum amount of methane you can make through this process, this non-biological process. And even with very generous assumptions, it still falls well short of what modern biology makes, right? And so based on the difference in the fluxes, you could hopefully distinguish these scenarios. And you can, of course, convert the flux to the observable you see, the abundance, and I just had a quick and dirty way of doing it. In practice, you'd want to use a detailed photochemical model, but I've swapped out the x-axis here with a rough calculation, and you sort of get the rule of thumb that anything greater than 0.5% methane is hard to explain with these non-biological processes. So just as for oxygen, where we have these possible scenarios for non-biological accumulation and their discriminants, I think what would be useful to have would be a similar kind of framework for methane as a biosignature. Different scenarios for its production and ways to discriminate those false positives. So the bottom line here is that you see a habitable zone planet. It's got CO2, it's got pretty abundant methane, it doesn't have a lot of CO or no CO. Then this is a pretty good biosignature. It's hard to explain that with known processes. You could even make the argument that this methane CO2 biosignature could be more common than oxygen or ozone biosignatures just because of the relative simplicity and complexity of those metabolisms. Right? I don't want to spend too long on this next part, but just to kind of help persuade the astronomers they might want to be interested in this, I wanted to talk briefly about the detectability of such a biosignature. So, let's pretend TRAPPIST-1e is like the Archean Earth. Let's give it lots of biogenic methane, lots of CO2, pretty much no CO. Let's calculate what its transit transmission spectrum would look like. let's put that in a James Webb instrument simulator and add some noise to it and then do the retrieval. How well can you see this thing? And so if you do that, so you do 10 transits with near-spec prism, an Archean Earth-like TRAPPIST-1e, this is the posteriors you get, right? So obviously this is a very simplified calculation, but it's encouraging, I think, that you can detect the CO2, you can put some crude abundance constraints on the methane and a rough upper limit on the CO with 10 transits. In principle, everything you need, you can observe everything you need to be able to rule out these false positive scenarios. And just as a comparison, right? So this is what you just saw, TRAPPIST-1e. As an Archean Earth, 10 transits, you can see the biogenic methane. If you instead suppose that TRAPPIST-1e is like the modern Earth, a lot of oxygen, a lot of ozone, 10 transits with whatever James Webb instrument you like, you can't see it. You can't detect the ozone. So not only is this methane CO2 biosignature potentially more common than oxygen biosignatures, it's also easier to detect, at least with James Webb. All right, so having given you that kind of optimistic perspective, I want to now balance it out with some crushing pessimism. So without getting into the weeds here, there's several lines of evidence that suggest that the productivity of the earlier biosphere was much less than the modern Earth, right? So that's what this figure is showing, estimates of productivity through time. And so if you don't have a very productive biosphere, there's a question as to whether you can actually outgas enough methane to be detectable or be distinguishable from non-biological sources, right? And so you can go through the cases. If your planet has oxygenic photosynthesis, but still has an anoxic atmosphere, as was the case on Earth for probably a few 100 million years, and is actually more likely to be the case for planets around M dwarfs, as Owen will tell you in a moment. If you have oxygenic photosynthesis, it's not a problem. You can be as productive as you like, you can make as much methane as you like. If your biosphere only has anoxygenic photosynthesis as its primary production metabolism, then I think you're probably still okay. There are ecosystem models like on the right that show that if you've got hydrogen-based photosynthesis, you can, in principle, still build up large methane abundances due to biology. However, if you just have a purely chemoautotrophic ecosystem, that is, you're not using light from your star at all, you've just got life living off whatever redox gradients are outgassed, then it may be more difficult. If you're not outgassing enough hydrogen, then you may not build enough methane to be detectable. There's also this question of CO as an anti-biosignature. I actually still think CO is a pretty good anti-biosignature, but and so the reason we say that the absence of CO is a good indicator is that it's easy food for microbes, right? CO should be eaten, and I think that's true for the most part. But Eddie does have this recent paper showing that in some situations, for example, if you had a biosphere with making oxygen, burning a lot of biomass, then you can get sort of moderate levels of CO despite life being there. And so I think, high CO, methane and CO2, that's probably pretty safe to say it's not life, but if there's a little bit of CO there, it gets ambiguous. I haven't dived into the detectability issues, but obviously, there's issues of systematics, there's stellar heterogeneity, clouds, hazes. I don't think any of those things should be a showstopper, but obviously they didn't go into the previous calculations you just saw. It would need to be considered. And then, more generally, I think, is just the difference between these two scenarios, right? So for oxygen, there's been a lot of work gone into building this diagram. There's many studies behind it. People have been thinking about oxygen false positives for decades. Whereas for methane, methane as a biosignature, there's a much more limited literature. There's a couple of papers, there's a few paragraphs and discussion sections mentioning the possibility, but for the most part, this hasn't been very deeply studied. And so I think we should be open to, the possibility of the failure of imagination, the fact that there could be other scenarios out there which haven't been considered. I think there's also just a fundamental difficulty here, and that for all the oxygen false positive scenarios, right? It's the atmosphere making the oxygen. There's no scenario that I know of where the interior of planets can belch out molecular oxygen. All the false positive processes happen in the atmosphere, which you can see. So the hope is that you can see the context in which that oxygen generation occurred. You can see the different contextual clues that help reveal what's going on. This is in contrast with methane, where for the most part, atmospheres don't make methane. The interior of planets make methane. It's hard to see that, right? It's hard to do the exogeochemistry to work through all these different scenarios and understand the context for the false positive generation. And so, you know, I've talked through kind of the obvious cases here, but this doesn't exclude kind of more exotic subsurface chemistry, post-magmatic processes that could be generating methane. So for that reason, you know, if you were to do an observation, show me a planet where you'd found a lot of methane, a lot of CO2, and not a lot of CO, I would be very excited. But I would want to see some sort of corroboration. I think, you know, whether it be surface pigments or seasonality, some other trace species in the atmosphere that's potentially biogenic, or ultimately, you know, isotopes, looking at carbon isotope differences, as Stephanie mentioned. I think it's, you would want to see that, just given the difficulty of seeing the context of where the methane is generated. So just to quickly wrap up then, I've hopefully convinced you that chemical disequilibrium, although it's not a kind of one-to-one, big disequilibrium means life, that's not the case, but I think it's still a useful conceptual framework for thinking about exoplanet biosignatures. The Earth has indeed had a large biogenic disequilibrium in its atmosphere-ocean system throughout its history, as shown in that figure. And particularly in the Archean, there was this disequilibrium with methane and CO2. And when you dive into it, you find that it's hard to make that without life. You can kind of go through the obvious scenarios. It's really hard to make methane and CO2 in a terrestrial planet atmosphere without biology. So this is a potentially useful exoplanet biosignature. And it's worth thinking about soon, because this is one of the few, perhaps the only biosignature you could detect with James Webb. And so with that, I'd be very happy to take questions.
I think Stephanie wants you to ask him this question.
Chemical disequilibrium may come from both photochemistry and biology. Is there a way to incorporate the effects of photochemistry into the free energy calculation to rule out this possibility?
Yeah, I mean, you're right. I think so. For that reason, that's why I'm saying given the ambiguity and possible explanations for disequilibrium, you have to do the photochemistry. You have to dive into the kinetics, not just in the atmosphere, but also what is being fluxed from the surface. And so that's the argument that it's biological ultimately comes from doing that kinetics. So I think that's the approach you have to take. Whether a more general kinetic framework could be developed comparable to kind of the Gibbs energy metric, I don't know. That's something I've thought about and haven't made a lot of progress with. So you know, maybe someone has some good ideas. But yeah, you need to get at the kinetics, the source fluxes to infer biology from disequilibrium.
Hi. So there was something on one of your slides about the Gibbs energy disequilibrium. I think you were showing what it was if you only calculated it for Earth's atmosphere and didn't include the ocean.
Yeah.
Is that correct?
I sort of didn't dwell on that, but let me find that figure again.
I guess my question is, if it sounds like you have to include the ocean species in chemistry in order to see.
Sure. Okay. So in terms of just this calculation, right? It's true that if you don't include the ocean, all you have in the atmosphere is the oxygen and methane. There isn't much methane. You don't get much free energy. But when you allow the atmosphere to react with the ocean, then there is, of course, this much greater energy. But I really, and so I guess it's true. If you wanted to say that nitrogen, oxygen, water is out of equilibrium, that's a disequilibrium biosignature, you obviously need to confirm the presence of a liquid water ocean somehow. You need to make that observation. In the case of the methane, CO2, nitrogen, water disequilibrium, I see that more as sort of a motivation for the kinetic argument. So although it's true that for those things to be out of thermodynamic equilibrium, you need to confirm the presence of an ocean, it doesn't really affect the kinetic flux argument for methane being a biosignature. So that's the distinction.
So I have another question on this figure. So you said that Mars is pretty well out of its free air equilibrium. What causes that?
Yeah, so Mars is an interesting case. So obviously we know what's going on. It's all photochemical. It's, the reason Mars has this large disequilibrium is the coexistence of photochemically produced CO and oxygen. Since Mars is thin, it's basically just a stratosphere. And so when you calculate, the Gibbs energy per mole of atmosphere, it's quite large because you've just got that. All photochemistry is happening in a lot of the atmosphere. We actually have another paper on Mars where we talk about this disequilibrium as an anti-biosignature because we know the CO is produced by photochemistry. If there was a large biosphere on Mars in the subsurface, we expect it to eat that. It doesn't seem to be doing that CO metabolism, and so you can put upper limits on the amount of biomass on Mars today, and it's like a few million blue whales worth of the standard unit of biomass. So that's another example of the ambiguity of disequilibrium. It can be a biosignature in some context, that when there's an uneaten free lunch, it can be a sign that no one's home.
Anyone else?